Welcome back to my channel, Predicting the Future. Today, we'll talk about a topic. Um, Today, I want to talk about two concepts. The one is positive recurrence, and the other is null recurrence. In the last video, when I was talking about Bitcoin, I talk about I used the I used the random walk model to uh, to find out the probability of attackers, the success rate of attacker in the mining process. Um, Today, I want to talk about more specifically about attacking process when the attacker and the honest knows they both have one half of the mining process. They have the same amount of mining process power, the same amount of mining power. So each one of them have a probability one half to be success of mining the next block. This is actually a random walk process. Usually, people will think about such process as a drunkman. A drunkman walking on a line with probability p to the right and 1 minus p to the left, and people are interested about what's the probability that this drunk man will eventually come back to the origin, and also what is the expected number of time will take for the drunk man to come back to state zero. And this is what we're gonna dig into in this theory today. At the end of the video, you notice that even you find out another one very interesting concept in probability is not every random variable has, if you sum up all the possible probabilities, it does not always has to be one. The standard definition of random variable, if you sum up all the possible values, say if the sample space is all integers, then you sum out all the integers and its probability of hitting each integer. It's one. That's the standard way of saying random variable. But today we're gonna look at a random variable where if sum up all the probability of that random variable of hitting one of the integers in the integer space, it's actually less than one. So that's something we are gonna talk about today. So let's begin about the random walk process. There's two very important properties of random walk. One is time homogeneity property, which means that given any state I and j, the probability of the process in time n has the same probability as it is when it's in time 0. So no matter what time it is, the probability of moving right or left to the probability to moving to the right with the probability p and to left to the probability 1 minus p never change, no matter what time it is now. So that's the homogeneity property. Another important property of random walk is spatial homogeneity property, which means that it's not only time homogeneous, but it's also space homogeneous, which means that it's not only at state 0 that no matter what time it is, the probability of moving to right or left is p and minus p doesn't change, but also that if you shift the state space, if you shift the state from 0 to any other state, the probability doesn't change, which means that if you're at state n, the probability of moving from state n to n plus 1 and the probability of moving to n minus 1 is the same as p and minus p when you are in state 0. So that's a spatial homogeneity property. So these two property basically defines the random walk process, and there's many interesting properties or that derive from these two properties. Another very basic property of random walk process is that if you look at the random walk process, it's actually um, a sum of identical independent random variables, Bernoulli random variables. So starting from 0, you move to right and 1 or left with probability p and 1 minus p. Let's say it is z0. Then the next step is z1, z2, z3. And the value at the state n is actually the sum of those z values. So let's say xn is the random walk process. The xn is actually the sum of those zi. And by the strong law of large numbers, the average value of the xn is actually converged to the expected value of that single identical Bernoulli random variable zi, or because it's identical, let's say it's z0, and it's almost surely, which means that with probability 1, the all sample you observe it will eventually comes to that single value, and the samples you observe outside that single value expected value of z0 has a probability of 0. So that's I call it the average moving speed. Why? Because that the convergence actually tells you the average speed of the random process that moves. So it's the average speed that Drunkman is moving to a specific location. So if expected value is z0, let's say it's now 0. If it's now 0, then it's actually the moving speed to one direction. If p is greater than one half, then it's moving to the right. If p is less than one half, then it's moving to the left on average to in a specific at this average speed. But if expected value of z0 is actually 0, that means that it's now moving. So that's what we call it's always recurrent. So the Drunkman will always come back to state 0. So that's the average moving speed. And next thing is if you look at the random walk process, all states. What I mean states in the random walk, in one-dimensional random walk, we're talking about one-dimensional random walk, is that all states communicates with each other. State 0 always can go to 0 state n. It can always go to state n minus 1. State n minus 1 can always go to another positive m state. So it all communicates. That means that if one of the state is recurrent, then the whole state is recurrent. If one of the state is transient, then all states are transient. This is the property we proved in one of the Markov chain theories. If you're interested, you can always check out my channel in the Markov chain playlist. Now, so come back to is the Markov if is the random walk process a recurrent chain or it's a transient chain? And because all the states communicate, so the random walk state space is actually a irreducible state space. So there's only one state space in the random walk process. Now, so our question is, so we only have to determine whether the state 0 is recurrent or transient. In the meantime, we're also interested to the expected time of the first return is finite or infinite. This is called positive recurrent and non-recurrent. If the expected value of the first time return is infinity, it's called null recurrence. If expected value of the first time return is less than infinity, it's called positive recurrent. So we're gonna use two methods to find out whether the Markov, whether the random walk is recurrent chain or it's a transient chain. And we're also gonna find out the expected value of the state zero. The first method we're gonna use to find out these two values is called, I call it binomial method. So let's imagine this random walk process starting from 0 and the process come back to 0. It will take it will always take even number of steps to come back to 0. That means that the all number of steps, the probability of all number of steps to come back to 0 is 0. And so from the last Markov chain process videos, we have a theorem said if the sum of the p 0 to the power n is infinity, that means it's a recurrent state. Or in the same case, if the sum of the p 0 to the power n is less than infinity, then it's a transient state. So let's look at the probability of p for the process starting from 0 and come back to 0 in two n steps. So this is actually a binomial process because in order for the process to start from 0 and come back to 0, it has to be n steps to, let's say, to the right, and then n step back to the left in any order. So that's it's a binomial process. So the probability p00 to the power 2n is actually the binomial 2n select 2n times the probability p to the power n times 1 minus p to the power n. And here we're going to use a Stirling formula to find the approximate value of the sum of the power, the matrix P. So n factorial is actually similar to n to the power n plus 1 divided by 2 times exponential power to the minus n times the square root of 2 pi. If we replace the factorial n factorial into the probability p to 0 to the power 2n, we get this formula. And the sum of this p is this form. So if p is equal to, if p is 1 over 2, then the numerator part, 4p times 1 minus p is 1. So numerator part is just 1. The denominator part is square root of pi times n. So we can remove the square root of pi. It's a constant, so we just have to look at the sum of 1 over square root of n, which is a divergent series. So we conclude that the sum of the p to 0 to the power 2n is infinity. Therefore, the probability of for the process to start from 0 to come back to 0 in finitely many steps is 1. So if that concludes that if the process is an evenly process, that is to the left and right has the same probability 1/2, then the whole random walk process is a recurrent chain. Otherwise, if p is not equal to 1/2, then the numerator part p 4p 1 minus p is less than 1. And so this theory we can is definitely less than, we can ignore the denominator part because we can just put it to 1. It's definitely less than 4p times 1 minus p. So we know that this theory is a finite theory. The sum of the theory is finite. So we know that sum of the p0 to the power 2n is finite. Therefore, the probability of start from 0 and to come back to 0 in finite many steps is less than 1. So this comes back to the early in the beginning of the video. Most every random variable has its probabilities are sum out to 1. And this is actually one example that the probability of all t0 equal to n for n belongs to integers is actually less than 1, which means that there is a positive probability that t0 is infinity. It's not, so the probability of t0 equal to infinity is a positive probability. So this is an example of a random variable that doesn't sum up to 1. However, the first method, binomial method, doesn't tell us the expected value of t0. So we're going to have to seek to another method. I call it a generating function method to find out the expected value of t0. So to begin, I'm going to give a couple of definitions and symbols. So I define row 0r, function of taking argument n, is the probability of the process starting from 0 to first time reaching state r in n step. And also let's look at the probability of t0 less than infinity, which is the sum of from n to n is equal to 0 to infinity of p probability t0 equal to n given the initial state is starting from 0. And that is the sum of row 0, 0, n. And the expected value of t0 is just n times the probability of t0 equal to n. And that is sum of n times row 0, 0, n. And the definition of a generating function. So we're going to use the generating function. So the generating function has some very interesting properties. And let's first define what is a generating function. So generating function of a random variable x is the expected value, is an x of s. So it's expected value of s to the power x. And that is the sum of n equal to 0 to infinity s to the power n times probability of x equal to n. And if we let s equal to 1, the generating function t, and the generating function of g t0 of 1 is actually probability t0 less than infinity. And the derivative of g to t0 to 1 is actually the expected value of t0. Why? It just take the, if you look at the expected the definition of generating function x t0, that is actually s to the power n times the probability of t0 equal to n. If we take the derivative of s, then s to the power n becomes n times s to the power n minus 1. And when we take s equal to 1, everything in the s to the power n minus 1 becomes 1, and that becomes n times probability of t0 equal to n. And sum of those becomes the expected value of t0. And if we take the derivative multiple times, let's say we take the derivative of n times, then the series, all the terms from 0 to n minus 1 becomes 0, and the nth term becomes n factorial times the probability of t0 equal to n plus the remaining term. And if we take let s to be 0, the remaining term becomes 0, and all left is the nth term, which is the n to the factorial n times the probability of x equal to n. So because of that, we know that we come out that the probability of x equal to n is actually equal to 1 to the power 1 to the factorial n times the nth derivative of g at a value at when s equal to 0. What it tells us is that the generative function actually determines the probability distribution, right? So the generative function here is very interesting. It's a one-to-one relationship with a distribution function, random distribution, random variable distribution. So if we can find the generative function of t0, then we can find the probability of t0 less than infinity, and we can find the probability of, and we can find the expected value of t0. So that's our goal. We want to find the generative function of t0. So we want to know the generative function g of t0 at s equal to 1 is equal to 1 or less than 1, which is because the generative function t0 at 1 is actually the probability of t0 less than infinity. We're going to do that in 3 steps. The first step is we want to find the generative function of tr where r is greater than 1. So we start from not state 0, not coming back to 0, but coming back to a state r where r is greater than 1. And then we're going to use generative function of tr to find the generative function of t1. Last, we're going to use the generative function of t1 to find the generative function of t0. And from there, we can find our results. So let's first find the generative function of tr for r greater than 1. So when r is greater than 1, we write down the so by conditioning on t1, we can write the row 0r, which is the probabilities of starting from 0 by first time reaching state r in n step. It's the summing of all the intermediate states. When k is equal to 0 to infinity, the probability of tr equal to n, given that t1 is equal to k, which t1 is what? T1 is the first time reaching state 1 times the probability of starting from 0 to state 1 in k step. So that's Bayes' rule, or the Markov chain rule that we used here. And we but the k doesn't have to be goes to infinity, because if k equal to n, the value of k could only go to n. When k is greater than n, the probability this term is actually 0. So we can just write the term as of sum from k equal to 0 to k equal to n. But the probability of p tr equal to n given t1 equal to k is actually the probability of starting from 1 to state r in n minus k steps, right? So t1 has used k steps. In order for the process to reach r in n step, that's actually n minus k step. We're gonna need to reach state r from 1 to r in n minus k step. So that's the probability. So that's row 1r taking value n minus k times row 10 k. And here we're gonna further simplify that. So we're gonna use the spatial homogeneity property of random walk. So the probability of starting from state 1 to state R is the same as starting from state 0 to state R minus 1. So that's what we found. So now we have the formula for rho 0R of n. Then we're gonna plug in that into the function, the general function of TR. So the general function of TR of S is sum of n equal to 0 to infinity S to the power n, rho 0R taking value n, and we'll plug in that previous formula. So that will become this term. Let's split the term S to the power n to S to the power k times the S to the power n minus k. And then we can split that. So we take the terms with k, that is S to the power k, and rho 0, 1 taking value of k, and put that into one term of from summon k from 0 to infinity. And then we put the rest of the term, which is S to the power n minus k, times the rho 0 R minus 1 take a value n minus k, summing those terms from n for n equal to k to infinity. And what this tells us, so for n equal to k, the second term here, we can just do a variable replacement. Replace for n equal to k, we can put it to be n equal to 0. So that changing the variable, we know that this is actually another general function. It's a general function of t r minus 1. And the first term here, the sum of sk to the power 0, 1 to the k, is general function of t1. So we get that the general function of tr is actually general function of t1 times general function of tr minus 1. So by induction, we can find out that the general function of tr is actually the general function of t1 to the power r. So now we find the general function of tr. The next step we want to do is we want to find the general function of t1. So general function t1 is the sum of n equal to 0 to infinity s to the power n, rho 0, 1, take a value n. And if we look at the rho 0, 1 to the taking value n, which is by conditioning, we're going to condition, this time we're going to condition on x1. So that will be the probability of t1 equal to n, given x1 equal to 1 times the probability p, which is at the x value of equal to 1, given x0 equal to 0, plus the probability of t1 equal to n, given x1 is equal to minus 1, the other direction, times probability q. Q is 1 minus q, q is actually 1 minus p. So let's look at let's further look at those two terms. So the probability of t1 equal to n, given probability x1 equal to 1, is 0 if n equal to 0, right? So if n equal to 0, there's no way that t1 can the probability the process can reach 1 in 0 steps. And also it's 0 if n is greater than or equal to 2, right? Because if x1 is 1, that means that we reach state 1 in one step, and that's done. And by the definition of t1 is the number of times, is the time, t1 is the time of the process first reach 1, right? So x1 is already given that we reach state 1 in one step. Then for t1 to equal to n, for n greater than equal to 2 is impossible. We already done. We already reached 1 at state 1 at time 1. So so that process is so the probability is 0 for n greater than or equal to 2. So let's look at the second term. So the second term is trying to find the probability of t1 equal to n given x1 equal to minus 1. Given that starting from 0, we know that the first step is we reach minus 1, and we want to know what's the probability of t1 we reach state 1 in n steps. That is the same as starting from state minus 1 to state 1 in n minus 1 time, n minus 1 steps. Why? Because we already used one step by taking from 0 to minus 1. And by the spatial homogeneity property of random walk, we can move that whole process from minus 1 to 1 to move it to one direction, to starting from 0 to state 2. So this property is actually has the same probability that the random walk first reach state 0 in first reach state 2 in n minus 1 times, given the initial state is 0. And that is the probability, so which means that the probability of t1 equal to n given x1 equal to minus 1 is the same as the probability of t2 equals n minus 1 given x0 equal to 0. So that is rho 02 taking value n minus 1. And this probability is 0 if n equal to 0, because there's no way you can reach state 2 in 0 step. And also for 1, there's no way you can reach state 2 from 0 in 1 step. So therefore, we know that, so by the conclusion, we know that the when n equal to 0, the probability of starting from 0 to 1 in n step is 0, because the first term is 0 and the second term is also 0. And when n equal to 1, the probability of rho 01 at n step is p, because the second term is 0, the first term is 1 times p. When n is greater than or equal to 2, we know that the first term is 0 and the second term is q times rho 02 taking value n minus 1. So and then we can put all those values into the general function of t1 of s, and that is the sum of n equal to 0 to n infinity s to the power n rho 01 n, and the first term is 0. When n is equal to 0, that term is 0. When n equal to 1, the term is p times s. And when n is greater than or equal to 2, so that will become the sum of n equal to 2 to infinity of this term. We take out the q and 1s out of the s to the power n, and that will become qs times the sum of n equal to 2 to infinity s to the power n minus 1 times rho 02 taking value n minus 1. And by changing the variable from n minus 1 to n, the sum can be written to be starting from for n to start from 1 to infinity. Also, we can put let this sum to start from 0, because the rho 02 in step 0 is actually 0. We talk about that. So the probability of starting from 0 to state 2 in 0 step is 0. So the whole term becomes ps plus qs times generated from t2 at value s. And from the first step, we know that generated function of t2 is generated function of t1 to the power 2. So that becomes ps plus qs times t1 power 2. And this is a quadratic equation. And we can there's two roots, 1 plus the square root of 1 minus 1 minus 4 qp to the power s to the power 2 divided by 2qs. The other term is changing the plus sign to minus sign. And only one of these two is valid. But and this solution must also satisfy the general function of t1 at state 0, when s is equal to 0, which is actually the probability of 0, 1 in 0 step, which is actually probability 0. So we're gonna, so this is a condition, this is a boundary condition. And also the limit of, if we look at the limit of the first value, gt1, the plus term, 1 plus the value of 1 plus square root of 1 minus 4qs, 4qp s to the power 2 divided by 2qs. For s equal to 0, this term is actually goes to infinity. So this term doesn't converge to 0 at all. So it's definitely not the plus term. So the solution must be 1 minus square root of 1 minus 4qs s to the power 2 divided by 2qs. Therefore, the probability of the first time reaching state 1 given initial state 0 is gt1 when s equal to 1, as we know, is the sum of n equal to 0 to infinity, rho 0, 1 taking value n, which is actually the probability of t0 less than infinity. So that's the probability of ever reaching state 1 from 0 in finitely many steps. And we plug in that gt1 formula, and that becomes 1 minus the absolute value of 1 minus 2q divided by 2q. And if q is less than or equal to 1/2, this is probability 1. If q is greater than 1/2, that becomes q divided by, that becomes p divided by q. If you ever watch my video where I talk about Bitcoin mining and use the random walk process to model the probability, you notice this is the same value that we found in that video. So last step, so we're gonna use gt1 to find gt0. So gt0 is, by definition, is the sum of n equal to 0 to infinity s to the power n, rho 0 at step n, and that is if we condition on x1, so that term becomes p t0 equal to n, given x1 equal to 1 times p plus p probability of t0 equal to n given x1 equal to minus 1 times probability q. And here we're going to use again the time and spatial property of random walk. So this term in the bracket becomes so the probability of starting from state 1 at time 1 of ever reaching state 0 in n step is actually the same of starting from state 0 to reach state minus 1 in n minus 1 steps. And the same, the second term here, the probability of x starting from minus 1 in time 1 ever reaching state 0 in n step is the same of starting from time 0 at state 0 or ever reaching state 1 at n minus 1 time. So the whole term becomes, we put the sum into the summation of these two terms. We separate these two terms into two summations. So that becomes the summation of n equal to 0 to infinity s to the power n times rho 0 minus 1, taking value n minus 1 times p, plus the sum of n equal to 0 to the infinity s to the power n and times rho 0, 1, taking value n minus 1 times q. And these two sum, if we take the one s out of each of these two terms, that becomes s times the generated function of t minus 1 plus the same as q times the general function of t1. So we know the formula for general function of t1, but we don't know the general function of t minus 1. But moving from 0 to minus 1 and moving from 0 to 1 is actually symmetric in distribution with P and Q swapped. So by swapping Q and P and Q in the formula of general function of T1, we can get the general function of T minus 1. So we get general function of T minus 1 is 1 minus square root of 1 minus 4qps to the power 2. This is the same as general function of T1 divided by the denominator is different. That becomes the general function T minus 1 becomes the denominator of this one becomes 2 times ps, not 2 times qs. Therefore, the general function of T0 is sp times the general function, the formula for general function T minus 1 times sq times the formula for general function of T1. We simplify that. We get that the general function of T0 is 1 minus square root of 1 minus 4qps to the power 2. So the probability of starting from 0 of ever reaching 0 in finite many steps for the first time is the general function of T0 when s equal to 1, and that is 1 minus the absolute value of 1 minus 2q. When q equal to 1/2, the state 0 is a recurrent state. Why? Because when q is equal to 1/2, rho 0, 0 is 1. When q is not equal to 1/2, the state is transient. Why? By the definition of transient, rho 0, 0 must be less than infinity, less than 1. So rho 0, 0 in this time is 2q when q is less than 1/2, and 2p when q is greater than 1/2. Both cases less than 1. But what about the expected value of T0? We know the formula of general function of T0, which is 1 minus square root of 1 minus 4qp s to the power 2. And we know on early time, we talk about the general function, the derivative of the general function give us the expected value of that random variable. So let's take the derivative of general function of T0. And that becomes 4qps divided by square root of 1 minus 4qps to the power 2. So in that case, when q is equal to 1/2, the expected value of T0 starting given x0 equal to 0 is the derivative for g T0 when s equal to 1. And in that case, this is infinity. All right. So when q is equal to 1/2, the denominator becomes 0, and numerator is a constant. And when q is not equal to 1/2, and the expected value of T0 is 4qp divided by 1 minus 4qp, which is less than infinity. But be careful here. Remember, we know that we talk about that in method 1 and also in method 2 the early time. The probability of T0 less than infinity is less than 1. It's not 1. So the probability of T0 less than infinity is actually the summation of probability of T0 equal to n for all n from 0 to infinity, not including the actual infinity value, because we know that when this is transient, this probability is less than 1, which means that there's a positive probability that T0 equal to infinity is greater than 0. So this expected value is not the actual expected value of t0. It's actually the expected value of t0 when t0 is taking finite values. Um, so this is what I want to talk about today. We actually see, we talk about basically those things. First, recurrent state can be classified as two different recurrent states. One is positive recurrent and null recurrent. Positive recurrent is, in our case, in this one-dimensional random walk, when q is equal to 1/2, the expected value of t0 is infinity. So that's the definition for null recurrent. And positive recurrent is the state 0 is recurrent, but the expected value of that t0 is finite. And it can be proved that if the Markov chain has a finite number of states, then and if the state is recurrent, if one of the states is recurrent, that state must be positively recurrent. Yeah, that's it. Thank you, everyone. Hope you like it.